Wait till you see the ROC and the AUC. They're cool, yeah, StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about ROC and AUC, and they're going to be clearly explained. Note: this StatQuest builds on the confusion matrix and sensitivity and specificity StatQuests, so if you're not already down with those, check out the quests. Also, the example I give in this StatQuest is based on logistic regression, so even though ROC and AUC apply to more than just logistic regression, make sure you understand those basics. Let's start with some data. The basics apply to more than just logistic regression. Make sure you understand those basics. StatQuest is based on logistic regression, so even though you're not already down with those, check out the quests. Also, the example I give in this StatQuest is based on logistic regression. Or maybe
Exploratory data analysis, or EDA, is a method used by data scientists to analyze data sets and summarize them.
wait till you see.
their main characteristics. It helps determine how best to manipulate data sources to get the answers you need, making it easier to discover patterns, spot anomalies, test a hypothesis, or to check assumptions. You know, in fact, it's quite a lot like hunting for buried treasure. Let me explain. Meet Nate, the treasure hunter, and Sophie, the data scientist. When it comes to treasure and insights, they both go about things in much the same way. You see, Nate, our treasure hunter, starts out by identifying a potential treasure trove location. In the same way, Sophie, the data scientist, starts by identifying a data set that looks promising. Nate, he then scopes out the area, looking for clues that there is indeed treasure to be found. And in the same way, Sophie looks at the data set, looking for patterns or anomalies that could be exploited. Our treasure hunter then starts digging, looking for the treasure. The data scientist starts manipulating the data, looking for hidden patterns. And finally, on a good day, Nate finds the treasure and brings it back to be enjoyed. And Sophie, well, Sophie finds the insights from the data set and brings them back to the business to be used. So when it comes to finding what they're looking for, treasure and insights, you could say that Nate and Sophie, well, they have a lot in common. So the main purpose of exploratory data analysis, or EDA, is to analyze and summarize data sets. Now, there are 4 primary types of EDA, which we can classify into 2 subgroups. So there's univariate as the first subgroup, and then there's multivariate as the second subgroup. Univariate data is data that can be described just using one variable, while multivariate can be described using multiple variables. Now, within univariate, there are actually 2 other classifications. There's non-graphical and graphical. The main purpose of univariate analysis is to describe the data and find patterns that exist within it. And since it's a single variable, it doesn't deal with causes or relationships. Now, common types of univariate graphics include stem and leaf plots, which show all the data values and the shape of the distribution. And there's also histograms. That's a bar plot in which each bar represents the frequency or proportion of cases for a range of values. Multivariate non-graphical, well, that is typically used for techniques that generally show the relationship between 2 or more variables of the data through cross-tabulation or statistics. And then multivariate graphics, well, some examples of that include group bar charts, which each group represents one level of one of the variables, and each bar within a group represents the levels of the other variable. There's also bubble charts, heat maps, and run charts as well. Now, some of the most common data science tools that we have available to use to create EDA, well, those include Python and R. Python and EDA can be used together to identify missing values in a data set.
If you can fit a line, you can fit a squiggle. If you can make me laugh, you can make me giggle. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about logistic regression. This is a technique that can be used for traditional statistics as well as machine learning. So let's get right to it. Before we dive into logistic regression, let's take a step back and review linear regression. In another StatQuest, we talked about linear regression. We had some data, weight, and size. Then we fit a line to it. And with that line, we could do a lot of things. First, we could calculate R squared and determine if weight and size are correlated. Large values imply a large effect. And second, calculate a p-value to determine if the R squared value is statistically significant. And third, we could use the line to predict size given weight. If a new mouse has this weight, then this is the size that we predict from the weight. Although we didn't mention it at the time, using data to predict something falls into the category of machine learning. So plain old linear regression is a form of machine learning. We also talked a little bit about multiple regression. Now we are trying to predict size using weight and blood volume. Alternatively, we could say that we are trying to model size using weight and blood volume. Multiple regression did the same things that normal regression did. We calculated R squared, and we calculated the p-value, and we could predict size using weight and blood volume. And this makes multiple regression a slightly fancier machine learning method. We also talked about how we can use discrete measurements like genotype to predict size. If you're not familiar with the term genotype, don't freak out. It's no big deal. Just know that it refers to different types of mice. Lastly, we can compare models. So on the left side, we got normal regression using weight to predict size. And we can compare those predictions to the ones we get from multiple regression, where we're using weight and blood volume to predict size. Comparing the simple model to the complicated one tells us if we need to measure weight and blood volume to accurately predict size, or if we can get away with just weight. Now that we remember all the cool things we can do with linear regression, let's talk about logistic regression. Logistic regression is similar to linear regression, except logistic regression predicts whether something is true or false instead of predicting something continuous like size. These mice are obese, and these mice are not. Also, instead of fitting a line to the data, logistic regression fits an S-shaped logistic function. The curve goes from 0 to 1. And that means that the curve tells you the probability that a mouse is obese based on its weight. If we weigh a very heavy mouse, there's a high probability that the new mouse is obese. If we weigh an intermediate mouse, then there's only a 50% chance that the mouse is obese. Lastly, there's only a small probability that a light mouse is obese. Although logistic regression tells the probability that a mouse is obese or not, it's usually used for classification. For example, if the probability a mouse is obese is greater than 50%, then we'll classify it as obese. Otherwise, we'll classify it as not obese. Just like with linear regression, we can make simple models. In this case, if the probability a mouse is obese is greater than 50%, then we'll classify it as obese. Otherwise, we'll classify it as not obese. Just like with linear regression, we can make simple models. In this case, we can have obesity predicted by weight. Or more complicated models. In this case, obesity is predicted by weight and genotype. In this case, obesity is predicted by weight and genotype and age. And lastly, obesity is predicted by weight, genotype, age, and astrological sign. In other words, just like linear regression, logistic regression can work with continuous data like weight and age, and discrete data like genotype and astrological sign. We can also test to see if each variable is useful for predicting obesity. However, unlike normal regression, we can't easily compare the complicated model to the simple model, and we'll talk more about why in a bit. Instead, we just test to see if a variable's effect on the prediction is significantly different from 0. If not, it means that the variable is not helping the prediction. We use Wald's test to figure this out. We'll talk about that in another StatQuest. In this case, the astrological sign is totes useless. That's statistical jargon for not helping. That means we can save time and space in our study by leaving it out. Logistic regression's ability to provide probabilities and classify new samples using continuous and discrete measurements makes it a popular machine learning method. One big difference between linear regression and logistic regression is how the line is fit to the data. With linear regression, we fit the line using least squares. In other words, we find a line that minimizes the sum of the squares of these residuals. We also use the residuals to calculate R squared and to compare simple models to complicated models. Logistic regression doesn't have the same concept of a residual, so it can't use least squares and it can't calculate R squared. Instead, it uses something called maximum likelihood. There's a whole StatQuest on maximum likelihood, so see that for details, but in a nutshell, you pick a probability scaled by weight of observing an obese mouse, just like this curve. And you use that to calculate the likelihood of observing a non-obese mouse that weighs this much. And then you calculate the likelihood of observing this mouse. And you do that for all of the mice. And lastly, you multiply all of those likelihoods together. That's the likelihood of the data given this line. Then you shift the line and calculate a new likelihood of the data. And then shift the line and calculate the likelihood again. And again. Finally, the curve with the maximum value for the likelihood is selected. Bam! In summary, logistic regression can be used to classify samples, and it can use different types of data, like size and or genotype, to do that classification. And can also be used to assess what variables are useful for classifying samples, i.e. astrological sign is totes useless. Hooray, we've made it to the end of another exciting StatQuest. Do you like the StatQuest?
If you feel confused, don't sweat it. StatQuest is here.
StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to cover another machine learning fundamental, the confusion matrix, and it's going to be clearly explained. Imagine that we have this medical data. We've got some clinical measurements, like chest pain, good blood circulation, blocked arteries, and weight. And we want to apply a machine learning method to them to predict whether or not someone will develop heart disease. To do this, we could use logistic regression, or k-nearest neighbors, or random forest, or some other method. There are tons to choose from. How do we decide which one works best with our data? We start by dividing the data into training and testing sets. Note, this would be an excellent opportunity to use cross-validation, and if you're not familiar with that, well, check out the StatQuest. Then we train all of the methods we're interested in with the training data, and then test each method on the testing set. Now we need to summarize how each method performed on the testing data. One way to do this is by creating a confusion matrix for each method.
The rows in a confusion matrix correspond to what the machine learning algorithm predicted, and the columns correspond to the known truth. Since there are only two categories to choose from, heart disease or does not have heart disease, then the top left corner contains true positives. These are patients that had heart disease that were correctly identified by the algorithm. The true negatives are in the bottom right-hand corner. These are patients that did not have heart disease that were correctly identified by the algorithm. the bottom left-hand corner contains false negatives. False negatives are when a patient has heart disease, but the algorithm said they didn't. Lastly, the top right-hand corner contains false positives. False positives are patients that do not have heart disease, but the algorithm says they do. For example, when we applied the random forest to the testing data, there were 142 true positives, patients with heart disease, that were correctly classified, and 110 true negatives, patients without heart disease that were correctly classified. However, the algorithm misclassified 29 patients that did have heart disease by saying they did not. These are false negatives. And the algorithm misclassified 22 patients that did not have heart disease by saying that they did. These are false positives. The numbers along the diagonal, the green boxes, tell us how many times the samples were correctly classified. The numbers not on the diagonal, the red boxes, are samples that the algorithm messed up. Now we can compare the random forest confusion matrix to the confusion matrix we get when we use k nearest neighbors. K nearest neighbors was worse than the random forest at predicting patients with the heart disease, 107 versus 142, and worse at predicting patients without heart disease, 79 versus 110. So if we had to choose between using the random forest and k nearest neighbors, we would choose the random forest. Bam! Lastly, we can apply logistic regression to the testing dataset and create a confusion matrix. These two confusion matrices are very similar and make it hard to choose which machine learning method is a better fit for this data. We'll talk about more sophisticated metrics like sensitivity, specificity, ROC, and AOC that can help us make a decision in the next stat quests. Now that we have the basic confusion matrix figured out, let's look at a more complicated one. Here's a new data set. We'll talk about more sophisticated metrics like sensitivity, specificity, ROC, and AOC that can help us make a decision in the next stat quests. Now that we have the basic confusion matrix figured out, let's look at a more complicated one. Here's a new data set. Now the question is, based on what people think of these movies, Jurassic Park 3, Run for Your Wife, Out Cold, spelled with a K, and Howard the Duck, can we use a machine learning method to predict their favorite movie? If the only options for favorite movie were Troll 2, Gore Police, or Cool as Ice, then the confusion matrix would have 3 rows and 3 columns. But just like before, the diagonal, the green boxes, are where the machine learning algorithm did the right thing, and everything else is where the algorithm messed up. In this case, the machine learning algorithm didn't do very well, but can you blame it? These are all terrible movies. Bam. Ultimately, the size of the confusion matrix is determined by the number of things we want to predict. In the first example, we were only trying to predict 2 things, if someone had heart disease or if they didn't. And that gave us a confusion matrix with 2 rows and 2 columns. In the second example, we had 3 things to choose from, and a confusion matrix with 3 rows and 3 columns. If we had 4 things to choose from, we get a confusion matrix with 4 rows and 4 columns. And if we had 40 things to choose from, we get a confusion matrix with 40 rows and 40 columns. Double bam! In summary, a confusion matrix tells you what your machine learning algorithm did right and what it did wrong. Hooray! We've made it to the end of another exciting stat quest. If you like this stat quest and want to see more, please subscribe. If I were in Hawaii, I'd be sitting on the beach, in the shade of a tree, watching StatQuest. Hello, I'm Josh Starman. Welcome to StatQuest. Today we're going to cover logistic regression, and we're going to dive deep into the details. This is part 1 of a series of videos I'm going to do on logistic regression. This time we're talking about coefficients. This StatQuest follows up on logistic regression clearly explained, which provides the big picture of what logistic regression is and how it works. In this video, I want to dive deeper into how logistic regression works. Specifically,
ROC and AUC. Yeah, cool. Yeah, StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about ROC and AUC, and they're going to be clearly explained. Note, this StatQuest builds on the confusion matrix and sensitivity and specificity StatQuests, so if you're not already down with those, check out the quests. Also, the example I give in this StatQuest is based on logistic regression, so even though ROC and AUC apply to more than just logistic regression, make sure you understand those basics. Let's start with some data. The y-axis has two categories, obese and not obese. The blue dots represent obese mice. Axis has two categories than just logistic regression. Even though ROC and AUC apply to more than just logistic regression, make sure you understand those basics. Apply to more than just logistic regression, make sure you understand those basics. Based on logistic regression. So, even the example I gave down confusion matrix and sensitivity and specificity StatQuests. So if you're not already down with those, check out the quests. Also, the example
When the well runs dry, you might be thirsty, but there's still StatQuest. You can watch it. StatQuest.
Hello, I'm Josh Starmer, and welcome to StatQuest. Today we're going to continue our series on machine learning fundamentals, and we're going to talk about sensitivity and specificity. They're going to be clearly explained. This StatQuest follows up on the one that describes the confusion matrix, so if you're not already down with that, check out the quest. The first half of this video will explain how to calculate and interpret sensitivity and specificity when you have a confusion matrix with 2 rows and 2 columns. And the second half will show you how to calculate and interpret sensitivity and specificity when you have 3 or more rows and columns. Even if you're already down with the confusion matrix, let's remember that rows correspond to what was predicted, and columns correspond to the known truth. When there are only 2 categories to choose from, in this case, the 2 choices were has heart disease or does not have heart disease, then the top left-hand corner contains the true positives. True positives are patients that had heart disease that were also predicted to have heart disease. True negatives are in the bottom right-hand corner. True negatives are patients that did not have heart disease and were predicted not to have heart disease. The bottom left-hand corner contains the false negatives. False negatives are when a patient has heart disease, but the prediction said they didn't. Lastly, the top right-hand corner contains the false positives. False positives are patients that do not have heart disease, but the prediction says that they do. Once we've filled out the confusion matrix, we can calculate 2 useful metrics, sensitivity and specificity. In this case, sensitivity tells us what percentage of patients with heart disease were correctly identified. Sensitivity is the true positives divided by the sum of the true positives and the false negatives. Specificity tells us what percentage of patients without heart disease were correctly identified. Specificity are the true negatives divided by the sum of the true negatives and the false positives. In the StatQuest on the confusion matrix, we applied logistic regression to a testing dataset, and ended up with this confusion matrix. Let's start by calculating sensitivity for this logistic regression. Here's the formula for sensitivity, and for true positives, we plug in 139. And for false negatives, we plug in 32. When we do the math, we get 0.81. Sensitivity tells us that 81% of the people with heart disease were correctly identified by the logistic regression model. Now let's calculate the specificity. Here's the formula for specificity. And for true negatives, we'll plug in 112. And for false positives, we'll plug in 20. When we do the math, we get 0.85. Specificity tells us that 85% of the people without heart disease were correctly identified by the logistic regression model. Now let's calculate sensitivity and specificity for the random forest model that we used in the confusion matrix StatQuest. Here's the confusion matrix. Here's the formula for sensitivity, and when we plug in the numbers, we get 0.83. Here's the formula for specificity, and when we plug in the numbers, we get 0.83 again. Now we can compare the sensitivity and specificity values that we calculated for the logistic regression to the values we calculated for the random forest. Sensitivity tells us that the random forest is slightly better at correctly identifying positives, which, in this case, are patients with heart disease. Specificity tells us that logistic regression is slightly better at correctly identifying negatives, which, in this case, are patients without heart disease. We would choose the logistic regression model if correctly identifying patients without heart disease was more important than correctly identifying patients with heart disease. Alternatively, we would choose the random forest model if correctly identifying patients with heart disease was more important than correctly identifying patients without heart disease. Bam. We get 0.85. Specificity tells us that 85% of the people without heart disease were correctly identified by the logistic regression. logistic regression model. Now let's talk about how to calculate sensitivity and specificity when we have a confusion matrix with 3 rows and 3 columns. The big difference when calculating sensitivity and specificity for larger confusion matrices is that there are no single values that work for the entire matrix. Instead, we calculate a different sensitivity and specificity for each category. So for this confusion matrix, we'll need to calculate sensitivity and specificity for the movie Troll 2, for the movie Gore Police, and for the movie Cool as Ice. Let's start by calculating sensitivity for Troll 2. For Troll 2, there were 12 true positives, people that were correctly predicted to love Troll 2 more than Gore Police and Cool as Ice. So for true positives, we'll plug in 12. And there were 112 plus 83, which equals 195 false negatives, people that loved Troll 2 but were predicted to love Gore Police or Cool as Ice. So for false negatives, we'll plug in 195. And when we do the math,
we get 0.06. Sensitivity for Troll 2 tells us that only 6% of the people that love the movie Troll 2 more than Gore Police or Cool as Ice were correctly identified.
if I were in Hawaii, I'd be sitting on the beach in the shade of a tree, watching StatQuest. Hello, I'm Josh Starman, welcome to StatQuest. Today we're going to cover logistic regression, and we're going to dive deep into the details. This is part 1 of a series of videos I'm going to do on logistic regression. This time we're talking about coefficients. This StatQuest follows up on logistic regression clearly explained, which provides the big picture of what logistic regression is and how it works. In this video, I want to dive deeper into how logistic regression works. Specifically, we'll talk about the coefficients that are the result of any logistic regression. We'll talk about how they're determined and interpreted. We'll talk about the coefficients in the context of using a continuous variable, like weight, to predict obesity. And we'll talk about the coefficients in the context of testing if a discrete variable, like whether or not a mutated gene, is related to obesity. Before we dive into the details, let's do a quick review of some of logistic regression's main ideas to make sure we're all on the same page. In this example, the y-axis is the probability a mouse is obese. It goes from 0, the mouse is not obese, to 1, the mouse is obese. If I were in Hawaii, I'd be sitting explained, which provides the big picture of what logistic regression is and how it works. In this video, I want to dive deeper into how logistic regression works. Specifically, we'll talk about the coefficients that are the result of any logistic regression. We'll talk about how they are determined and interpreted. We'll talk about the coefficients in the context of using a continuous variable, like weight, to predict obesity. And we'll talk about the coefficients in the context of testing if a discrete variable, like whether or not a mutated gene is related to obesity. Before we dive into the details, let's do a quick review of some of logistic regression's main ideas to make sure we're all on the same page. In this example, the y-axis is the probability a mouse is obese. It goes from 0, the mouse is not obese, to 1, the mouse is obese. The dotted line is fit to the data to predict the probability a mouse is obese given its weight. If we weight a heavyweight mouse, then the corresponding point on the line indicates that there's a high probability, close to 1, that it is obese. And if we weight a middleweight mouse, then there's an intermediate probability, close to 0.5, that it is obese. Lastly, a lightweight mouse has a low probability, close to 0, of being obese. Okay, those are all the basics we need for this StatQuest. One last thing before we get started. I want to mention that logistic regression is a specific type of generalized linear model, often abbreviated GLM. Generalized linear models are a generalization of the concepts and abilities of regular linear models, which we've already talked about.
I give in this StatQuest is based on logistic regression. So,
about in many StatQuests. That means that if you're familiar with linear models, then you're well on your way to understanding logistic regression. We'll start by talking about logistic regression when we use a continuous variable like weight to predict obesity. This type of logistic regression is closely related to linear regression, a type of linear model. So let's do a super quick review of linear regression. Shameless self-promotion. If you're not already familiar with linear regression, check out the StatQuest on linear regression and linear models part 1. Okay, we start with some data, and we fit a line to it. And this is the equation for the line. It has a y-axis intercept and a slope. And we plug in values for weight to get predicted values for size. So, even though we didn't measure a mouse that weighed 1.5, we can plug 1.5 into the equation and predict that mouse to have size 1.91. And a mouse with weight 1.5 and size 1.91 would end up on the line at this point. Now, even though it's silly, the equation can predict the size of mice with weight equals 0. That's just the y-axis intercept, 0.86. And we can even predict the size of mice with negative weights. I'm pointing this out because the fact that we are not limiting the equation to a specific domain and range makes it easier to solve. And this has a big effect on how logistic regression is done. So, over on the left side, we have linear regression, and on the right side, we have logistic regression. With linear regression, the values on the y-axis can, in theory, be any number. Unfortunately, with logistic regression, the y-axis is confined to probability values between 0 and 1. To solve this problem, the y-axis in logistic regression is transformed from the probability of obesity to the log odds of obesity. So, just like the y-axis in linear regression, it can go from negative infinity to positive infinity. So we can see what we're doing. Let's move the logistic regression to the left side. Now let's transform the y-axis from a probability of obesity scale to a log odds of obesity scale. We do that with the logit function that we talked about in the odds/log odds StatQuest. P, in this case, is the probability of a mouse being obese and corresponds to a value on the old y-axis between 0 and 1. The midpoint on the old y-axis corresponds to p equals 0.5. And when we plug p equals 0.5 into the logit formula and do the math, we get 0, the center of the new y-axis. Here is p equals 0.731 on the old y-axis. If we plug p equals 0.731 into the logit function and do the math, we get 1 on the new y-axis. If we plug p equals 0.88 into the logit function and do the math, we get 2 on the new y-axis. If we plug p equals 0.95 into the logit function and do the math, we get 3 on the new y-axis. Lastly, these blue points from the original data are at p equals 1. If we plug p equals 1 into the logit function and do the math, well, technically you can't divide by 0. However, the log of 1 divided by 0 equals the log of 1 minus the log of 0. And the log of 0 is defined as negative infinity. And since something minus negative infinity equals positive infinity, this whole thing is equal to positive infinity. This means the original samples that were labeled obese are at positive infinity on the new y-axis. As a result, the original y-axis from 0.5 to 1 is stretched out from 0 to positive infinity on the new y-axis. Similarly, 0.5 to 0 on the old y-axis is stretched out from 0 to negative infinity on the new y-axis. Ultimately, we end up with the log of the odds of obesity on the new y-axis. And the new y-axis transforms the squiggly line into a straight line. The important thing to know is that even though the graph with the squiggly line is what we associate with logistic regression, the coefficients are presented in terms of the log odds graph. In the StatQuest, logistic regression details part 2, fitting a line with maximum likelihood, we'll talk more about how this line is fit to the data. But for now, just take my word for it that this is the best fitting line. Just like with linear regression, the best fitting line has a y-axis intercept and a slope. The coefficients for the line are what you get when you do logistic regression. The first coefficient is the y-axis intercept when weight equals 0. It means that when weight equals 0, the log of the odds of obesity are negative 3.476. In other words, if you don't weigh anything, the odds are against you being obese. Duh. Here's the standard error for the estimated intercept. And the z-value is the estimated intercept divided by the standard error. In other words, it's the number of standard deviations the estimated intercept is away from 0 on the standard normal curve. That means that this is the Wald's test that we talked about in the odds ratio StatQuest. Since the estimate is less than 2 standard deviations away from 0, we know it is not statistically significant. And this is confirmed by the large p-value, the area under the standard normal curve that is further than 1.47 standard deviations away from 0. The second coefficient is the slope. It means that for every 1 unit of weight gained, the log of the odds of obesity increases by 1.825. Here's the standard error for the slope. Again, the z-value is the number of standard deviations the estimate is from 0 on the standard normal curve. And again, the estimate is less than 2 standard deviations from 0, so it is not statistically significant. This is no surprise with such a small sample size. And this is confirmed with the large p-value. Double bam! Now we know all about the logistic regression coefficients when we use a continuous variable like weight to predict obesity. Now let's talk about logistic regression coefficients in the context of testing if a discrete variable, like whether or not a mouse has a mutated gene, is related to obesity. On the left side, we have mice that have a normal gene. And on the right side, we have mice with a mutated gene. Just like before, some of the mice are obese, and some of the mice are not obese. This type of logistic regression is very similar to how a t-test is done using linear models. So let's do a quick review of how a t-test is done using linear models. Shameless self-promotion. If you're not already familiar with how a t-test can be performed using a linear model, then check out the StatQuest, Linear Models Part 2, T-Tests and ANOVA. Okay, we start with some data. In this case, we've measured the size of mice that have a normal gene, and the size of mice with a mutated version of that gene. Then we fit two lines to the data. The first line represents the mean size for the mice with the normal copy of the gene. The second line represents the mean size of the mice with the mutated copy of the gene. These two lines come together to form the coefficients in this equation. The mean value for size for the mice with the normal copy of the gene goes here, and the difference
even though our Hey everyone, welcome back. So today we're going to be talking about the ROC curve, which officially stands for the receiver operating characteristic. Now the reason I didn't write that whole phrase on the board is because it's not very helpful. Just a quick history lesson, it was called that because it was initially used by the US Army to see whether or not they're doing a good job of predicting enemy aircraft. So we're going to do a little bit of example that's more relatable today. So let's say that you are running a business called Statflix. So Statflix hosts movies about statistics for people to watch, and you have a bunch of different users. Now in any such subscription service, one big problem is called churn. So churn happens when you are at risk of an existing customer leaving. So they might be leaving for various reasons. Maybe they don't use your service enough. Maybe it's too expensive for them. But either way, churn is something that businesses try to predict really well. And the reason is because when you think about keeping an existing customer versus signing on a new customer, it's much cheaper to keep the existing customer. So if that existing customer is going to leave, we can try to give them some free things. We can be like, oh, here's a free month. Here's $5 off of your plan or something. And we can try to get them to stay because that's going to be easier for us than losing them and trying to sign on someone completely different. So today we're going to be using that as our example. We're going to be trying to predict churn. And the whole goal of this video is not the model itself. We'll see that gets explained pretty quickly. The whole goal of this video is judging whether the model and the predictions that we get from the model are good or bad. And we'll see how the ROC curve factors in just a moment. But first, let's go through the beginning, the machine learning framework. So let's say you have a big data set of customers and you split them up into a training and testing set. You use the training set to build the model, as always. And we won't worry about the model, just it could be anything. Let's just say it's a logistic regression to be simple. And that gets called M. Now you use your model M, which was built on the training set, and you feed in your testing set, which your model has never seen before. And you output some probabilities for every single customer in the testing set for how likely we predict that customer is to churn. So we get some probability between 0, which means the customer is very likely not to churn, versus 100%, which means the customer is very, very likely to churn. Now, we're actually not done, because if we actually want to make some kind of decision, we want to decide which customers to send free things to and which to not send free things to, we as the data scientists need to do one last thing. We need to draw a line somewhere between the 0 and 100 called a cutoff or a threshold, which says that everyone to the left of that line does not get any freebies, and everyone to the right of that line does. For example, just to keep things simple, let's say I drew the line there around 50%. That would mean that if my model has a less than 50% chance of you churning, I'm not going to send any free things to you. I'm just going to assume you won't churn. But if my model has a greater than 50% chance that you're going to churn, I will try and keep you as a customer by offering you things, okay? And that threshold is really up to us. As we'll see, when we change that threshold, interesting things happen. Now, before we get to that, let's look at an old friend called the confusion matrix. Now, I have a video on the confusion matrix, which I'll post below, but it's pretty easy to understand. It's just a simple 2x2 matrix where the rows are whether the customer will actually churn or not actually churn, so churn versus not churn, and the columns are whether we predict that customer to churn or predict them not to churn. So C and NC4 are the columns. And just to relate this back to what I drew above, everyone in the C, so everyone in the predicted churn, would be everybody who is to the right of this black line, and everyone in the predicted not churn would be everyone to the left of that black line. Now, each of these components has a special name. So the two that we would like to maximize are called true positives. This means that these are people who would churn, and we predicted they would churn. This is probably best case scenario, so we can try and keep these people as customers. The next best one is true negative, which means that these people will not churn, and we predicted they will not churn, so we don't unnecessarily send them free things because they wouldn't have churned anyway. Now, the most disastrous one is called false negative. These are people who would actually churn, but we did not catch them, so we did not send them any free things, and we probably would lose them as customers. And another bad one is called false positive. So these are people who would actually not churn, but we thought they would, so we sent them resources unnecessarily. Okay, so these are the 4 components of the confusion matrix. Now we're going to start talking about how the ROC curve starts gaining its form. The ROC curve says, okay, I'm going to take these 4 components and I'm going to derive 2 metrics from there. 2 metrics that tell a very interesting story. The first of those metrics is called the TPR, or true positive rate. And the calculation is pretty simple. The calculation is just TP over TP plus FN. So let's look at the table again to get an idea of what that actually means in real world terms. So that's basically only looking at the top row. So notice this calculation only takes into account things in the top row. So this calculation is answering the question of all the people that will churn, that's the top row. What percentage do I catch? This is also sometimes called the recall. So obviously this is something I want to maximize, right? Because I'm saying that of all the customers that will churn, I want the percentage that I catch and that I could send resources to be very high. So I want to maximize my true positive rate. Now the other metric is based on the bottom row, and that is based on all the customers that would not actually churn. And this is called the false positive rate. A very similar calculation, and the story here is that we divide FP by the sum of the 2 cells in the bottom row. Now this answers the question of all the customers that will not churn, how many do I predict incorrectly? That's why the FP is the numerator here. And clearly I would like to minimize this because I want that error rate to be small. So the ROC curve begins its story by saying I have this TPR and FPR, and I would like to maximize my TPR and minimize my FPR. Now we can also plot these. Since these are only 2 metrics, it's pretty easy for us to plot in a simple 2-dimensional space. So here's that plot. Both of these metrics clearly are running between 0 and 1. They're bounded between 0 and 1. So we can put FPR on the x-axis and TPR on the y. y-axis. Now, a couple things I'll note is that what's the best case scenario? The absolute best case scenario would be if TPR was 1, so we catch everybody who's going to turn, and FPR was 0. So our error rate on people who will not turn is 0. And that graphically is at this start up here.
Now let's calculate the specificity for troll 2. There were 23 plus 77 plus 92 plus 17 equals 209 true negatives. People that were correctly predicted to like Gore Police or Cool as Ice more than troll 2. So for true negatives, we'll plug in 209. And there were 102 plus 93 equals 195 false positives. People that loved Gore Police or Cool as Ice the most, but were
So in today's video, have you ever tried to do exploratory analysis in a project and gotten stuck on questions like, how do I know how far into this analysis I'm actually supposed to go? How do I know if I'm looking at the right things or even taking the right approach? And now I have 10 tabs open in Excel and a bunch of SQL.
Hey guys, my name is Shashank Lalonathy. I'm a data analyst, and on this channel, I teach you all the skills necessary to become a data analyst, and you can follow me on my journey to become a data scientist. Today, we're going to be going over the book Practical Statistics for Data Scientists, Chapter 1. In this series, I'm going to go over the first 3 chapters of this book because the subsequent chapters, the information there is covered in my hands-on machine learning guide, which is also in my channel. You can see that linked in the video. Hey guys, my name is Shashank Lalonathy. I'm a data analyst, and on this channel, I teach you all the skills necessary to become a data analyst, and you can follow me on my journey to become a data scientist. Today, we're going to be going over the book Practical Statistics for Data Scientists, Chapter 1. In this series, I'm going to go over the first 3 chapters of Hey guys, my name is Shashank Lalonathy. I'm a data analyst, and on this channel, I teach you all the skills necessary to become a data analyst, and you can follow me on my journey to become a data scientist. Today, we're going to be going over the book Practical Statistics for Data Scientists, Chapter 1. In this series, I'm going to go over the first 3 chapters of this book because the subsequent chapters, the information there is covered in my hands-on machine learning guide, which is also in my channel. You can see that linked in the video. If you're at all interested in following along with this book, feel free to buy it using the Amazon affiliate link I have below. You should get the same price as normal, but I would a small commission in exchange for you clicking on the affiliate link. Before we get started, I'm going to have some notes I'll be showing you along with some code and recommending if you're all interested in supporting the channel and you would like access to the notes, then feel free to follow me on my Patreon. It's a great way to support the work and show that what I'm doing is helpful for you. Without further ado, let's go ahead and get started. So I'm
Wait till you see the ROC and AUC. They're cool, yeah, StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about ROC and AUC, and they're going to be clearly explained. Note, this StatQuest builds on the confusion matrix and sensitivity and specificity StatQuests, so if you're not already down with those, check out the quests. Also, the example I give in the StatQuest is based on logistic regression, so even though ROC and AUC apply more than just logistic regression, make sure you understand those basics. Let's start with some data. The y-axis has two categories, obese and not obese. The blue dots represent obese mice, and the red dots represent mice that are not obese. Along the x-axis, we have weight. This mouse is not obese, even though it weighs a lot. It must be Mighty Mouse and just full of muscles. This mouse doesn't weigh that much, but it is still considered obese for its size.
Hello, welcome to Moo Moo Math, where we upload a new math video every day. In this video, I'd like to talk about two types of quantitative data, discrete and continuous. Discrete data is data that has distinguishable spaces between the values. Often, it is data that is counted. On a graph, the ordered pairs are at specific locations, so the graph is not connected, but only points. Some examples of discrete data would be the number of dogs, number of people, the number of tickets that you have for a show. Continuous data is data that falls on a continuum. On a graph, it includes all the points
In this video, we're going to talk about the difference between continuous data and discrete data. Now, continuous data is data that can take on any value in an interval, whereas discrete data, it can only have specific values. So let me give you an example. So let's say we have the interval 1 to 10, or we can write this. So let's say that x is a value between 1 and 10. Now, in a continuous set of data, x could be 1, it could be 1.3, it could be 2.46, it could be 5.389, it could be any value between 1 and 10. Now, on the right side, when dealing with a discrete set of data, x can only have specific values. For example, it may only have values that are whole numbers, such as 1, 2, 3, 4, 5, and so forth. So here it only has specific values, not values like 3.46 or 4.75. Now, continuous data is data that can be measured. So if you're measuring something, it's not only going to be whole numbers, it can be decimal numbers or fractions. Discrete data is data that is counted, and it's very easy to count whole numbers and natural numbers. So a good example of continuous data would be, let's say, temperature, because you can measure the temperature on any given day. For instance, today it might be 83.6 degrees Fahrenheit, or tomorrow, let's say in the desert, it might be 99.46 degrees Fahrenheit. So this is something that can be measured. On the right side, let's say if you're rolling a 6-sided die, the only numbers that you can get are discrete values, 1, 2, 3, 4, 5, or 6. If you roll a 6-sided die, you can't get 2.37 or 4.6, because it can only take on specific values. And so that's a very simple way to distinguish continuous data from discrete data. Now what we're going to do is go over some examples. So for each of these situations, would you say it represents a continuous set of data or a discrete set of data? Let's start with number 1, the speed of a car. Would that be continuous or discrete? Now, the speed of a car, we say it can be measured or counted. The speed of a car can be measured. A car could be going at 25.6 miles per hour, it could be going at 30 miles per hour, or it could be going at 42.86 miles per hour. And so it doesn't have to take on specific values, it can be any value. Therefore, the speed of a car would represent a continuous set of data. Now what about number 2, the number of cats in a neighborhood? Can that be measured or counted? In this case, you can count the number of cats in a neighborhood. In your neighborhood, you might be able to count 5 cats, or 12, or 18. You can't really have half a cat. I mean, that would just be wrong. So this set of data can only have whole numbers. In this case, this would be a discrete set of data. Now what about your body weight? Your body weight is something that you can measure. A person could be 160 pounds in weight, or they could be 173.4 pounds in weight. So that can vary. It doesn't have to be specific values, it could be any value. So that would be C for continuous. The number of doctors in town. You can't have half a doctor or a quarter of a doctor. You have like 8 doctors in town, 12 doctors in town, 17 doctors in town, so this would be discrete. Now what about the number of books on a shelf? And that can be counted as well. So therefore, that represents a discrete set of data. Now the height of a student. You can't really count the height of a student, you can measure it. A student might be 6.3 feet tall, they could be 5.84 feet tall, so that can be measured. So we're going to say C for continuous. The number of students in the classroom, that can be counted, like the number of doctors in town, so that's going to be discrete. Now what about number 8 and
StatQuest. Hello, and welcome to StatQuest. StatQuest is brought to you by the friendly folks in the genetics department at the University of North Carolina at Chapel Hill. Today we're going to be talking about what a distribution is. Imagine you're at a wild and crazy dance party, and you overhear someone talking about statistics. Chances are they're going to be talking about distributions. Dag! What is a statistical distribution? Imagine we measured the height of a lot of people. The first person we measured was 5.2 feet tall, so we put that measurement in a bin that spans from 5 feet to 5.5 feet. The second person we measured was 5.8 feet tall. The third person we measured was 5.6 feet tall. The fourth person we measured was 5.9 feet tall. The fifth person we measured was only 5.1 feet tall. And the sixth person we measured was 6.3 feet tall. Okay, you get the idea. We measure a bunch of people and put the measurements in bins. When you stack a bunch of measurements into bins like this, you get a histogram. Most of the measurements come from people between 5 and 6 feet tall. People smaller than 5 feet tall were relatively rare. People taller than 6 feet tall were also relatively rare. In other words, if you picked one measurement at random, there's a good chance it would be between 5 and 6 feet tall. The histogram gives us a sense of how likely we'll measure someone really tall or really short or closer to the average. What if we use smaller bin sizes for our measurements? Now the bins are half as wide as before. And here's how our data stacks up in the smaller bins. Again, most measurements are between 5 and 6 feet tall, but we can be more precise and say half the people are between 5.25 feet tall and 5.75 feet tall. By measuring more people and using smaller bins, we get a more accurate and more precise estimate of how heights are distributed. We can use a curve to approximate the histogram. The curve tells us the same thing that the histogram tells us. There's a low probability that we will measure someone shorter than 5 feet tall. There's a low probability that we will measure someone taller than 6 feet. Lastly, there's a relatively high probability we'll measure someone between 5 and 6 feet tall. However, the curve has a few advantages over the histogram. First, even though we measured a bunch of people, we didn't get a value for this bin. Since we can't calculate that probability with the histogram, does that mean we will never get a measurement that fits into that bin? No. Lastly, if we expect a curve, show where measurements are less.
If a 60% free throw shooter takes 10 shots, what is the probability that it makes exactly 7 of them?
If we were looking to understand the spread of player heights in the NBA, we may well use a normal distribution, where the continuous numerical height data from the population of NBA players is distributed symmetrically around the mean. In other words,
If a 60% free throw shooter takes 10 shots, what is the probability that it makes exactly 7 of them? To answer questions like that, we can use this formula for the binomial distribution. And this doesn't just apply to free throws. It applies whenever there's a repeating process where you could put the outcomes into 2 categories. That's where the bi in binomial comes from. And that kind of situation is pretty common considering it encompasses all yes or no questions. The formula looks a bit scary, but by the end of this video, we'll make sense of it. And hopefully it's pretty along the way. Okay, we're gonna start with one blob. It's programmed to make it 60% of the time, so what's the probability that it would make 1 out of 1? This question feels a little bit silly. We don't need any fancy formulas to know that the answer is 60%, but it's a starting point to build on. Another silly starting question is, what's the probability it makes 0 of 1? It's the other 40% of the time. 60% is the same as 3 out of 5, so we can visualize the probabilities by looking at 5 blobs and having 3 of them make it and 2 of them miss. Okay, now what if the blobs take 2 shots each? It'll be helpful to have more blobs to look at here, so let's make this into a square of blobs and have the new blobs also take their first shot, again with 3 out of 5 of them making it. And then they can all take a second shot, which means we now have to ask about making 0, 1, or 2 of 2 shots. You might notice this isn't exactly random, but for the moment we're just focusing on making a clean diagram. 4 of the 25 blobs were unlucky enough to miss both the first and the second shot. From this, we can say that a 60% free throw shooter has a 16% probability of missing both shots. And this is the same number we would have gotten
by multiplying the probabilities of the individual shot outcomes. The probability of missing the first shot is 40%, then 40% of those 40% also miss the second shot, and 40% of 40% comes out to 16%. Next, for the blobs that made one shot, we have two groups. One group of 6 made the first and missed the second shot, and 6 out of 25 is 24%. Again, we can multiply the individual probabilities to check that they come out the same, and indeed, 60% for the make times 40% for the miss comes out to 24%. The second group is pretty much the same, except the make and the miss come in the opposite order. And adding these together, we get a 48% probability for making one of two shots. And for the ones that made both shots, there's again just one group, and we can fill in the numbers in the same way. And all these probabilities add up to 100%, which is a great sign. We're gonna add a third shot in a moment here, but it might already be possible to guess at the pattern. So try pausing and see if you can predict what it's gonna look like after 3 shots. Okay, for the third shot, it'll be useful to have even more blobs to look at, so let's make this a 3D grid and have the new blobs take their first 2 shots. With 3 shots, the top 3 layers made it and the bottom 2 layers missed. It's a little bit difficult to see what's going on inside this cube, so let's pull it apart into sections and organize it by outcome. Okay, so again, there's only one way to miss all of the shots. 8 of the 125 blobs ended up in this category, which gives us a probability of 6.4% for that outcome. And again, we could get this same number by multiplying the probabilities of the individual misses. Next, for one make out of 3 shots, there are 3 ways to get it. The first way in this list is miss, miss, then make. 12 of the 125 blobs had this outcome, which gives us a 9.6% probability. Multiplying the individual probabilities looks like this. The thing to notice here is that all 3 of these groups have the same number of blobs in them. The probability is the same for each of them. We don't care about the order of makes and misses, we just care about how many there are. And order also doesn't matter for multiplication, so each of these comes out to the same 9.6%, which means we don't have to go through all the different ways of making one of 3. We can just calculate the probability for one of them, then multiply that result by 3 to get the overall probability of making 1 out of 3 shots. And this idea will come in handy for looking at 2 out of 3. Just like before, there are 3 groups, and they each have the same probability, which is 14.4% each, for an overall probability of 43.2% to make 2 out of 3. And for 3 out of 3, there's just one way with a probability of 21.6%. So we have this pattern of counting the number of specific ways to make a certain number of shots, and then multiplying that by the probability for each of those specific ways, which again are always the same. And that's exactly what this formula does. This bit here stands for the number of ways to get k makes out of n total shots. It's called the binomial coefficient. In this example we just went through, the binomial coefficient is 1, 3, 3, or 1, depending how many makes we're asking about. We don't yet have a great way of finding it for other numbers of attempts and makes, so most of the rest of this video is going to focus on that. And the second part is multiplying the probabilities of the individual shots. This little p is the probability of a success, so 60% in this case, and 1 minus the little p is the probability of a failure, so 40%. And if we write these calculations so far using exponents, you can start to see how they have the same shape as the formula. So this formula has a lot of pieces and a lot of letters, so depending how much practice you've had with algebra recently, it might feel a bit overwhelming. If so, I can guarantee you're not alone. And it might be a good exercise to pause, take out a piece of paper, and plug the numbers into the formula for each case yourself. Now, all the math nerds out there are going to yell at me, with good reason, if I don't mention that this formula only makes sense if the shots are independent of each other, which might not be true. For example, missing the first shot might make you nervous, changing the probability of making the next shot, making things way more complicated. For the rest of this video though, we're going to assume that the interactions between shots are minor enough that we can ignore them. And these blobs don't even have the memory of a goldfish, so every shot is a fresh start. That might sound lazy, but even if you care about making the most accurate model possible, it's usually good to start with a simpler model, then test it to see how it performs, then add complexity if you need to. Alright, so now we have the overall structure of the formula figured out, but we're not quite ready to answer that original question about making 7 of 10 shots. We can plug in the numbers, but it's not clear just yet how we count how many different ways there are to arrange 7 makes and 3 misses. Okay, let's start fresh, forgetting about the probabilities, and just focus on counting the ways each number of shots could be made, which again is called the binomial coefficient. Starting with a blob that hasn't taken any shots yet, there's only one possibility, where it's made 0 shots. When the blob takes a shot, there are 2 possible branches reality can take. One where the shot goes in, and one where the shot misses. And this is true every time we add a shot. For the second shot, these 2 possibilities split into 4 possibilities. 1 possible way of missing both shots, 2 possible ways of making one of the 2, and 1 way of making both. So just like before, we have this 1-2-1 pattern after 2 shots. The neat thing about this table is that both ways to make 1 out of 2 shots are tracked together. The tree of blobs over on the right tracks every single possible order of makes and misses, but the number of blobs we have to draw is going to double every time we add a shot. Since we only care about the total number of makes, lumping them together in a table is good enough and it makes the tracking a lot easier. And adding a third shot, we get the same pattern we found before with 1, 3, 3, and 1 ways to get each total of successes. But now it's going to be a lot easier to add a 4th shot. We can just continue the pattern of pushing the numbers down the table and combining them. So for 4 shots, it looks like there's still just 1 way to miss them all, 4 ways to make 1, 6 ways to make 2, four ways to make 3, and 1 way to make all 4. And we can just continue this pattern to find any number we need. So now we could use the binomial distribution formula to answer this question from the very beginning of the video. What is the probability a 60% free throw shooter will make 7 of 10? We can look at this table to see that there are 120 ways to make 7 out of 10 shots. And the probability for each of those ways happening is 0.6 to the 7th power for the 7 makes, times 0.4 to the 3rd power for the 3 misses. On the outside of each row are 1 and each number in the middle is found by adding the 2 numbers above it. So we now have a way to get this binomial coefficient for any numbers, but it's still a lot of work, especially if the numbers are big, so it would be nice if there were a faster way to do it. The good news is there's a formula for the binomial coefficient. The bad news is it looks like this. Those exclamation points are called factorials. If you haven't seen them before, I think it's easiest to explain them with examples. 1 factorial is 1. 2 factorial is 2 times 1. 3 factorial is coefficient. Take the previous unique object, there are n.
We as humans are quite awful at truly conceptualizing numbers in our minds. We don't really know what a number is, but we can associate it with something we do know, and that helps us understand it. If I say 1,000,000 units of water, be that liters or gallons, we don't know how much that is. I can then show you that 1 million liters or gallons is equivalent to this, and now we have an idea of how much a million of something is. 52 factorial is a number. A very large number, actually. So large it doesn't fit in a human's world, no matter how you try to represent it. Therefore, it's normal to be skeptical when I tell you, after properly shuffling a deck of cards, with absolute certainty, that sequence of cards has never existed before in the history of time. It certainly feels wrong, doesn't it? We don't understand numbers, but we understand a deck of cards. I mean, we can hold
n factorial ways to do it, and that's where the n factorial in the numerator of this makes and misses. Remember blobs. And we'll take the perspective that we only care about whether the blobs are wearing